It's not simply enough to configure a few VLANs on a switch and think you're done. You need to be able to connect devices to your switch. And for that matter, you need to be able to connect switches together. So in this video, we're going to look at interfaces, specifically the types of interfaces that you might see, the problems you might face, and how you can troubleshoot them. Switches come with various types of interfaces. The most common ones you will see are RJ45 and transceivers. This is the RJ45 cable. RJ45 refers to the connector on the end of the cable, not the cable itself. The cable is known as a CAT cable. There are various CAT standards like CAT5 and CAT6. These are the cables that you will commonly use to connect devices like workstations, printers, some servers, and so on. We commonly see these types of connections running at 1 gigabit, but they can also run at 10 gigabit. This is a transceiver port. It's different as we can add a transceiver to the switch to control what that port does. Basically, a transceiver is a hardware module that we buy and insert into the switch. This means that we can use different transceivers to achieve different goals. For example, we may have a transceiver to connect two switches using fiber optic cable at 10 gig. Or we may use another transceiver to connect our servers to our switches using copper cabling. Or we may have a different transceiver again to connect two different buildings together using long-range fiber at 1 gigabit. The advantage is that we can mix and match the types of interfaces we use in a single switch. These transceivers use standards like SFP, SFP+, and QSFP. An SFP transceiver supports 1 gig, while an SFP Plus supports 10 gig and sometimes 25 gig. QSFP, or Quad SFP, is a larger connector, which is used for higher speed applications. It's really just 4 SFP Plus transceivers joined together, so it can handle speeds from 40 to 400 gig. But even though they're different physically, they operate in much the same way. For example, we can configure both of these port types with VLANs, IP addresses, and things like these. This is why we see a separation between the layers of the OSI model. The details at layer 1 can be different, while layers 2 and 3 can be the same. One physical difference worth noting is that the RJ45 CAT type of cabling supports different interface speeds, for example, 100 meg, 1 gig, 10 gig, and others. When two devices are connected, they will negotiate the best speed that they can both run at. This means that one device may need to slow down to support the other device. This is a feature called auto negotiation, and it's on by default. It's particularly useful on a switch where a variety of different devices connect. We can override this and set the speed manually if we want to. To do this, we first enter interface configuration. Let's add a description while we're here just to show how it's done. Then we disable auto negotiation with the no negotiation auto command. The speed is set with the speed command. If we use a question mark, we can see the different speeds that this interface supports. For our example, let's set this one to 100 megabit. Transceivers are a bit different. They are physical modules that are installed into the switch port and are hard-coded to a certain speed. I learned this the hard way years ago, when I had a 10 gig switch and a 1 gig ASA firewall. I used a copper DAC cable to connect them. The DAC cable, as shown here, is a copper cable with a transceiver built into each end. Sometimes they're known as twin-ax cables. Anyway, the problem is that the transceivers on both ends were hard-coded for 10 gig, but the firewalls would only support 1 gig. I thought I could use the speed command to change the switch end to 1 gig to match the firewall, but it just doesn't work that way. Transceivers have a fixed speed that we can't change. When two devices are connected to each other, they can operate in full duplex or half duplex mode. In full duplex mode, the interface can send and receive at the same time. In half duplex mode, it can only send or receive at any given time. As you can imagine, full duplex is far more efficient. These days, full duplex is used in most cases. In fact, for interfaces to operate at 10 gig or faster, full duplex is mandatory. On interfaces 1 gig or slower, we can change the duplex mode. I don't often do this, but sometimes you'll be asked to try it for troubleshooting. Let's try changing a few interfaces to half duplex mode. we can configure a range of interfaces using the range keyword. This can save us a bit of time. Just as before, we need to start by disabling auto negotiation. You can probably guess that under normal circumstances, two devices will work out if they want to use full or half duplex, just like they did when negotiating speed. Using the duplex command, we can see the different options that we have. Not many really, so let's just set these interfaces to half duplex. Even though we will use full duplex wherever we can, you will find that in many cases, service providers will still use half duplex in some cases. When a service provider deploys a fiber service to your premises, which could be for internet, voice, WAN, or something else, they can use either one or two cores of fiber as shown here. If there are two cores, one will be used for sending data, while the other is used for receiving data. That makes it full duplex. On the other hand, they may only give you one core of fiber. In this case, it's half duplex, as it can send or receive, but not both at the same time. I'm not 100% certain why they do this. I think it's because it's so expensive to run new fiber in conduits underground. When they're running new fiber, they'll usually run a lot more than they need so they can connect more customers later. So if they run, let's say, 144 cores of fiber along the street, they can support 144 customers at half duplex, or only 72 at full duplex. In the end though, they're still able to get the speeds that they promised to you over a single core. What if auto negotiation were to fail? In this case, there are a few rules that interfaces need to follow. First, they'll use the slowest supported speed, which is usually 10 meg. Rule number 2 is if the speed is 10 or 100 meg, it will set half duplex. And rule number 3, for other speeds, use full duplex. Cisco switches have the ability to sense the speed of other switches, so if auto negotiation fails, they will try to set the speed accordingly. But if that fails, they'll fall back on the rules we've just discussed. Where we can run into trouble is if one side is full duplex and the other is half duplex. This is known as duplex mismatch. This could happen due to a fault or due to a configuration error on our part. When operating in half duplex, the rules are the same as when connected to an old hub. It needs to use carrier sense multiple access collision detection to detect collisions. Full duplex, on the other hand, doesn't need to use that. So therefore, if one side's in full duplex and the other side's in half duplex, one side will use CSMA and the other won't. The half duplex side will think there are collisions when there aren't, and it will run the back-off algorithm, it'll resend frames and so on. The ultimate result is that the link will kind of work, but it will have degraded performance. Here are 2 questions for you to consider. Pause the video now if you can and have a think about them, or come back later and give them a try some other time. I'm sure you're aware that all data is broken into manageable chunks before it's sent over the network. We often call these chunks of data packets, which is fine. Technically though, at layer 2 they're called data frames, and at layer 3 they're called packets. There's a few reasons for breaking our traffic into packets. For one, if there's more than one path to a destination, some packets could take one path and some could take the other. More importantly though, if some packets are dropped, it's easier to detect this and resend a few packets rather than resending everything. Or for some traffic types, it's sometimes okay just to ignore a few missing packets. So the big question we have is, how big should each packet be? The Ethernet standard says that a normal frame should be no larger than 1518 bytes, or 1522 bytes if it includes a VLAN tag. That includes all data and headers. There are normally 18 bytes of headers, or 22 with a VLAN tag, so the payload, that's the data that goes inside the frame, can be up to 1500 bytes. Sometimes we'll enable a feature called jumbo frames. This allows us to grow the maximum frame size to around about 9000 bytes. There are pros and cons to this, which I won't get into right now. Just be aware that jumbo frames exist, which allow us to put more information into a single frame. So as mentioned, inside the frame we have a payload, which is probably an IP packet. This, in turn, has its own headers and a payload. The largest IP packet, including payload and headers, that an interface can send is called the MTU, or Maximum Transmission Unit. As I said before, this is 1500 bytes by default. On a rare occasion, we might want to change this value. For instance, if a device along the path somewhere can't handle a packet this big. Or we might use a technology that adds more headers to the packet or frame, which leaves less space for the payload. We'll see an example of this when we look at VPNs later in the series. So let's take a look at how we might change the MTU on a switch's interface. This, of course, is under the interface configuration. Then we simply use the MTU command, followed by the size. So naturally, you'll be wondering, what happens if a device tries to send a packet that's larger than the MTU? Remember that the MTU could change somewhere along the path too. If this happens, then the packet will need to be fragmented. This is where the device takes the packet that's too large and it's broken into smaller pieces. So each of these pieces is smaller than the MTU limit. The receiving device will then take all these fragments and reassemble them into the original packet. In short though, we don't want fragmentation. This impacts performance by making various devices work harder than they need to. So where you can, configure the MTU correctly. And if you don't need to change it, just leave it as it is. What about enabling jumbo frames on your internet connection? Do you think that's possible? Have a think about it, maybe do some of your own research and see what you can find. Consider discussing it in the comments section if you want to. Okay, let's get a bit more practical and see how we can confirm if our interfaces are working correctly. First, we'll take a look at what interfaces we have with Show Interface Description. These are the descriptions we add to interfaces during configuration. Here we have an interface connecting to a router and another interface connecting to a switch. Now we'll get some high-level information with Show Interface Status. In the port column, we can see the interface itself, and right next to that is the name or description. The status column tells us right away if the interface is connected to something or not. If this does not say connected, you probably need to check if the cable is connected at both ends. The VLAN column will show the VLAN ID if this is an access port, or it will show trunk if it's a trunk port. The duplex column shows if this interface is in full or half duplex. If there's an A here, it means that the interface is configured using auto negotiation. And the speed column, it's much the same. Finally, the type column. This shows the interface type, which will vary depending on what interfaces are available in your switch or router. Another way we could look at it is with Show Interfaces Summary. This shows the interfaces over on the left, as well as a lot of counters. The key to understanding the counters is listed above the table, but let me summarize. The first three columns are queues. These are holding areas for packets while they're being processed. These values should stay fairly low. If these start growing, then your switch is not processing packets fast enough. The next four columns are the receive and transmit rate in bits per second and packets per second. Anything with an RX refers to the receive rate, while TX is transmit. As you can see, not much is happening on this switch right now. If we see that rates are approaching the limit of the link, then it might be time to upgrade the link. So imagine that we suspect a particular interface is causing problems. We can dig deeper into this with Show Interfaces, followed by the interface that we want to look at. In our case, Show Interfaces GI0/1. This brings up a lot of information, which can be intimidating at first. For now, we'll just pick out some of the interesting bits. In the first line, we can see that the interface is up, and the line protocol is also up. The interface being up refers to the physical interface. If this is down, then the cable is most likely unplugged. If it's listed as administratively down, then we've manually shut down the interface ourselves. If the interface is down, then the line protocol will also be down. If the interface was up and the line protocol was down, then this might indicate a cable fault or a mismatch in configuration between the two devices. If this happens, check the speed, duplex, and trunk settings and make sure they're the same between both ends of the link. On the next two lines, we can see the interface type, such as Gigabit Ethernet, the MAC address and burned-in address, and the description. The following two show us the MTU of this interface, as we discussed earlier, the bandwidth of this interface in kilobits per second, so 1 million would be 1 gig, and then reliability, TX load, and RX load. These are values out of 255, which sounds weird, but it's just because it's an 8-bit number. Reliability refers to how many packets this interface is dropping. We want this number to be 255, which means it's 100% reliable. TX load and RX load is how much of the bandwidth is being used for transmitting and receiving. That means a load of 255 means the interface is at 100% capacity, which would not be a good thing. Further down the list, we can see the duplex setting, which should usually say full duplex, the speed, such as 1000 megabit per second, and the media type. Much of this is the same information we got from our other commands. There are often several different ways to get the information we need. Just past halfway, we can see the 5-minute averages of the input and output rates. Sometimes we have high levels of traffic in short bursts, and other times we might have high levels for a long time. So if the 5-minute average is quite high, then we have a sustained high traffic rate. If it's regularly near maximum, then we need to look at upgrading our links. The large section at the bottom includes various counters. This includes how many packets and bytes an interface has received and transmitted, and how many are using multicast. There are a lot of other counters too. Collisions, which are when Ethernet collisions have occurred. This might happen if you have an old-fashioned hub in place, or sometimes it'll happen if a cable is longer than it should be. Runts are packets that are discarded because they're too small. That is, less than 64 bytes. This is generally a byproduct of collisions, so once again, look out for hubs or cables that are too long. Giants are packets that are discarded for being too big. That is, if the frame is bigger than 1518 bytes and it can't be fragmented for some reason. CRC means the checksum on the frame has failed. This could be because the frame is being corrupted somewhere, or there's a bad cable, or the cable is too long, or there's interference from an outside source. There's a lot of information here, and I understand this can be overwhelming. So here's a pro tip. We can filter the output to just show the parts we're interested in. Firstly, we can pipe any command through the include command. This only displays the lines that match our input. If you're familiar with Linux, this is like a simplified version of grep. Here, we're filtering our previous output to only show lines that include the word rate. This makes it much simpler if we know what we're looking for. We can even use this to look at the data rates for all interfaces at once. But notice that it hasn't given us the interface name when we do this, which makes it a bit hard to tell which interface has a high data rate. So we can get a little bit fancy. The include command uses regex. If you're not familiar with what regex is, well, it's simply an advanced method for matching things. So what we can do is use include and then put the words rate and Ethernet inside brackets. Notice that they're separated by the pipe character. In regex language, this means or. So we're asking to see any line that includes the word rate or the word Ethernet. This tidies things up a bit. Okay, here's the next tip. First, look at the counters for interface gig 0/1 again. There's a lot of counters and maybe a lot of errors, but how long have they been here? Do these represent a current problem, or does it represent a problem that happened a month ago or a year ago? What we can do is we can clear these counters with the clear counters command. This can be done for all interfaces or just the ones we want. Now we can look at the counters again and see if the error counts are going up or are they staying at 0. If they're going up, then that means we're seeing a problem right now. Here's an interesting question for you to consider. Can you see what might be wrong with this interface based on this output? Here's another opportunity for you to test your skills in the lab. This is the same topology as the last video, so I'm sure you're comfortable with it. This time, the customer has reported network issues. You have been given the task of collecting troubleshooting information, as well as shutting down redundant interfaces. Are you up to the challenge? When we connect multiple switches together, we need to consider the impact of loops in the network. Spanning tree is the technology that helps us to manage this. So, in the next video, we're going to take a look at how spanning tree works in detail.